Welcome back to Edupedia World. Today we will be starting a new chapter, that is a chapter on electromagnetism. And in the initial lecture today we will see what is known as Oersted's experiment, which defines, or he was the first person to show that any current carrying wire produces a magnetic field of its own, hence electromagnetism. Then next we will see the current carrying wire, a straight current carrying wire, how does it produce a magnetic field. And finally we will close the lecture with what is known as the right hand thumb rule, which gives the direction of magnetic field produced by any current carrying wire. So let's start this interesting discussion. Our discussion today will be focused on the magnetic effect of electric current, that is how the electric current results in magnetic fields and magnetic effect. To begin our discussion, we will see what's known as the Oersted experiment. This was carried out by a scientist who goes by the name Hans Oersted in 1820, and he was the first person to demonstrate experimentally that any current carrying element will produce a magnetic field of its own. A wire, if it carries current, will have a magnetic field produced due to the current being carried. Okay, and this magnetic field which is being produced by the current carrying element is detected by the use of a compass needle, that is a magnetic needle. So this is the basic layout of Oersted experiment. What he did is that he attached a battery to a wire, and when the connection is switched on, that is the switch is on and the circuit is complete, current will flow from the positive terminal to the negative terminal. Okay, these two are parallel concepts. Here the positive is here, negative is here, here vice versa. So basically the current's direction is opposite in both the cases. Let's consider this particular case. Now what he observed was that when the current was flowing in this direction and a magnetic needle was placed below the wire, below this wire, if there were no magnetic field present, then the magnetic compass would have pointed in the south-north direction. This is my south-north, this is west, this is east. So ideally, in the absence of any magnetic field, the compass should direct towards the Earth's magnetic field, that is south-north. But as a result of this passing current, what he observed was if the magnetic compass was placed below the wire, then the north of the needle started deflecting towards west. So it, instead of being absolutely south-north, it became something like this. So northwest, let's say, southeast northwest. That was the case when the magnetic needle was placed below the current carrying wire, when the current is being carried in this direction. Next what he did is he kept the circuit the same, that is the current is flowing from this end to this end, but now he placed the magnetic needle above. Okay, so he placed the magnetic needle somewhere like this. What he saw as a result was that now instead of the magnetic needle pointing towards the west, it started pointing towards east. So basically it started pointing in this direction, that is this way. So now the direction of movement of the magnetic needle changed from the initial case where it was below. This brought to the conclusion that the direction of magnetic field generated by the wire is opposite at the bottom and above the wire. So the direction of magnetic field is opposite if we placed it below the wire than if we place it above the wire. Next, what he did was he switched the polarity of the battery. That is, he made this the negative terminal and this the positive terminal. As a result, the direction of current changed. Now the direction of current was this instead of this direction. What he observed is that a phenomena just opposite to the first case was observed here. That is to say, if the magnetic needle was placed below the wire, now instead of pointing south to north, it started pointing, the magnetic needle started pointing a little towards the east, that is to northeast. Okay, this implies that when the current is flowing from here to here and the magnetic needle is below, then the direction of magnetic field is opposite to the direction if the current was flowing from this direction to this direction. Similarly, he extrapolated the experiment and put the magnetic needle at top. Okay, so ideally in the absence of any external magnetic field, it should point south to north. But now in the presence of magnetic field, what happened is that it started pointing like this, that is towards northwest. So again the parallel concept here. Therefore, what we can conclude is that depending on the direction of motion of current and where the magnetic needle is placed, the magnetic movement can be either towards the west or towards the east. It will basically depend on which direction the current is flowing and with respect to that where the magnetic needle is placed. Okay, now how do we exactly determine what is the direction of magnetic field created due to the current carrying wire? Obviously there is a trend in the direction of magnetic field which we can observe from here, but what determines, how can we say without even using a magnetic needle that okay, the magnetic field here is going from this direction to this direction or from this direction to this direction? So we will see that in our next discussion. This discussion basically brought into light the fact that current carrying wire has a magnetic field of its own, and experimentally it was proved like this. Okay, now next let's see the magnetic field and the magnetic field lines due to a current carrying wire in a straight current carrying wire. That will help you gain insight into how to find the direction of the magnetic field. Let's do that. Let us now discuss what is the effect of current in a straight wire on the magnetic properties. So for this particular experiment, what is done is that iron fillings are kept on a cardboard which is placed horizontally, and a hole is made through the cardboard, and a wire is straight current carrying wire is passed through the hole. So this is my complete setup where I have provided some batteries here for current generation. There is a switch, and this segment of the wire is a straight wire passing through the hole, and random iron fillings are sprinkled over the cardboard sheet. Now what is observed is as soon as the current is switched on, in this case, the case on the right, the current will start flowing from the positive terminal, go through here, go downwards in the straight wire and end up at the negative terminal. This is you already know this clearly as a matter of fact. But what is interestingly observed is that the iron fillings will rearrange themselves in concentric circles. So you will see many different circles of iron fillings. They will basically circle up with the wire at the center. So this wire will be at the center of the concentric circles that is formed by the iron fillings. Now what is the reason for that? The reason is that this current carrying wire produces a magnetic field around it which is concentric in nature. So any point at a equal distance from the center will have same magnetic field, and it will have different magnetic field at a different distance, but if the same radius is observed, the magnetic field strength is the same at the same radius distance. Okay, now when the current is flowing from top to bottom, what we observe is that if we place a magnetic needle, then the north-south direction will be something like this. It will be something like this. This will be my south and this will be my north. Okay, and this way all the fillings will be surrounded, but the magnetic needle shows me the actual direction of the magnetic field. South north. If now I bring the magnetic needle over here, what I will observe is that now this becomes the south and this becomes the north. So basically anywhere around this concentric circle, the first, while going in the clockwise direction, first we will encounter the south and then we will encounter the north. Okay, this is the condition when the current is flowing. Flow of current is from top to bottom. Now suppose we reverse the polarity of the battery such that now the current flows from bottom to top, and we keep everything else the same. What you will observe is that the iron fillings remains as such. They will maintain their concentric circle pattern. But what change we will observe is that if we place the magnetic needle now, the magnetic needle will point in the opposite direction. This will now become my south and this will become north. Okay, so basically only the direction of magnetic field is changing, but the magnitude, if the magnitude of the current is same, only the polarity is changed, then the iron fillings remains stagnant in the concentric formation which it was initially. Therefore what we can say is changing the direction of the electric current changes the direction of the magnetic field. Okay, so this gives you an insight into how the magnetic field is produced. They are produced in concentric circles with the direction that can be that depends on the direction of motion of current. Now suppose you increase the amount of current flowing through the wire. Okay, through this wire, if you increase the amount of current flowing, what will happen is that the magnetic strength will increase, and also the distance till which the magnetic field is felt will increase. This will result in the concentric circles coming further closer. Since the magnetic strength has increased, the iron fillings will be more clustered around the wire. But also, since the magnetic field has increased at larger distance too, the iron fillings at a larger distance will also feel the magnetic strength now, the magnetic field. Therefore, by increasing the current flow, the amount of current flowing, we can increase the magnetic field strength at closer distance as well as at further distance, and that is manifested as increase in the concentration of the iron fillings close to the wire, as well as orientation of the iron fillings much further away from the wire. Increasing the current, magnitude of current, will not change the direction of the magnetic field. Direction of the magnetic field will depend only on which direction the current is flowing. Okay, so this gives you an idea about what influence the increase in current intensity will do. Now one point which I have not mentioned till now is that basically the earth has also a magnetic field of its own, isn't it? And this current carrying wire produces a magnetic field of its own. So the effective distribution of the iron fillings may not be a exact concentric formation, rather it will depend on the combination of the two magnetic fields. suppose that the magnetic field due to the current carrying wire is much larger than the Earth's magnetic field, then the ion fillings will be in exact concentric formation. But if the magnetic field produced by the ion current carrying wire is less because of less amount of current being flowing, then the direction of magnetic field will be combination of magnetic field due to the wire and the Earth's magnetic field, and that might result in the arrangement of ion fillings being not perfectly concentric in nature. Also, the point where the magnetic field due to the Earth's magnetic field and the magnetic field due to the current carrying wire are equal, exactly equal and opposite in direction, that will result in zero magnetic field at that point, and such a point is known as the neutral point. There, at that point, there will be no effect on a magnetic needle. If we place a magnetic needle at the neutral point, there will be no effect on the magnetic needle. Okay, so this gives you an idea about current in a straight wire. Now let us see how to find out the direction of magnetic field in a current carrying wire. For that, we'll use what is known as the right hand thumb rule. So this is the diagram for my right hand thumb rule, or what is alternatively known as the right hand grip rule. What this says is that suppose we have a current carrying wire. Okay, this is a current carrying wire in which the current is flowing from bottom to top. What you need to do to find the direction of the magnetic field is that hold the current carrying wire in such a way such that the thumb of the right hand points along the direction of the current. You need to know that you are using your right hand, and under that circumstance, if you curl your other fingers, so basically when you curl your other fingers, the fingers come like this, isn't it? So the direction of curling of your fingers will give you the direction of magnetic field at any point. So if we see from top, what we'll see is the fingers are being curled in an anti-clockwise direction, right? If you observe from top, then you see the direction of fingers being curled is in anti-clockwise direction. Therefore, at any point, let's suppose this point, what will be the direction of magnetic field? The direction of magnetic field will be in this direction, that is tangential to the concentric circle here. Whereas, if we consider this point, the curling will take it in this direction. So now the direction of magnetic field will be in this direction. Okay, so this simple rule, this simple right hand thumb rule easily gives you the direction at which the magnetic field will be produced due to a current carrying wire. Okay, let us extrapolate this and see how this is behaving in this scenario. Here our current is flowing from top to bottom. So if you point your thumb downwards and you curl the fingers, then what you will see is that the direction of magnetic field is in this direction, isn't it? If you observe from top, you will see it in clockwise direction. Whereas in this case, since the current is going from bottom to top, your thumb pointing upwards and you curling the finger will produce the direction of magnetic field in anti-clockwise direction as seen from top. That is what was shown here. Okay, so this right hand thumb rule is a very simple way to find out the direction of current, the direction of magnetic field due to a current carrying wire. Okay, so today's lecture I introduced you to the concept that any current carrying wire will produce a magnetic field of its own. We saw the Oersted's experiment to reveal this. Then next we learned about the experiment of a magnetic field generated by a straight current carrying wire using the ion filling experiment. And then finally we moved on to the right hand thumb rule to decide the direction in which the magnetic field will be produced. Next lecture we will see what is the magnetic field produced due to a loop. How is the behavior of magnetic field produced by a current carrying loop, and also we will see what is how the magnetic field is produced in a solenoid. So hope you are there to learn about these things in the next lecture. Till the next lecture, have a great day. Goodbye.